video is going to help us working with vectors and the forces of two vectors. Realize that, again, the resultant force, the sum of two vectors, can represent simple situations in the real world. So let's just show you a couple examples here. That's what we're going to kind of do in this video. First of all, if we had a rope tied to a tree, let's say we were trying to pull a tree down, right? So two men are trying to pull on two ropes attached to a tree. Well, obviously they're not going to attach the ropes and pull directly against each other. They'll get in each other's way. So what they're going to do is they're going to take that tree, and again, one of them is going to pull with a force of 40 pounds. The other one's 35 degrees, right? Different. Now notice we're not worried about the direction of the final vector. All we want is the magnitude. So what I'm going to do is I'm going to make this simple, and I'm going to attach my rope, one of them pulling directly to the right with a 40-pound force, which just means we can draw a vector for that, or write a vector for that, that's literally 40, 0, right? Just a simple component vector traveling to the right. However, the 50-pound force, right, needs to be 35 degrees off of that. So I'm going to imagine that's up into quadrant 1. I'm going to draw a 50-pound force, right, so a little bit longer than the red one. But again, if I wanted to represent that vector, now I would say that, hey, I'm pulling with a 50-pound force, and I'm going to have to use a trig form here. Remember that that's always cosine of your angle, which would be 35 degrees for us, and the sine of our angle, 35 degrees. Okay. Well, the resultant vector, remember, is just the resultant adding those two vectors together, or if we kind of drew the 50 pounds and drew the 40 pounds, right, the resultant vector is going to be that diagonal, right, through the middle, that parallelogram idea. Which means if we want the resultant, I'm just going to take 40 plus 50 cosine at 35, comma, 0 plus 50 sine at 35, right? I'm just finding one resultant vector, so I'll call that vector R, right? Now, we can find those values, which wouldn't be a bad idea. So let's go ahead and hop on our calculator real quick, and we'll figure out what those values are going to be, right? So I'm going to clear this out of here. We're just going to say 40 plus 50 cosine, again, of 35 degrees. And notice I'm in degree mode, so I'm in good shape there. So that's 80.958. Let's go ahead and write that down. Approximately 80.958, which makes sense. We're going a little farther to the right, right? We worked our way over here for that resultant vector. In fact, more than doubled the 40, right? That 35-degree angle wasn't much, so 50 is really helping the 40. Then we can hop back to our calculator again and type in 50, the sine of 35. Remember, there's no vertical component from that first vector. So 28.679, 28.679. But now remember, we want the magnitude, right, for our final answer. So we want to find the magnitude of vector R, which is going to be the square root of 80.958 squared plus 28.679 squared. But now, since those are rounded numbers, I'm going to use a little bit more precision. I'm actually just going to be careful typing in my calculator here. I'm going to say second the square root of, and I'm going to put that statement that I had, right, the unrounded, how I found my number, statement, my original form here, squared, plus, and let's do the same thing for the vertical component. I'm going to put in that 50 sine 35 squared. That's our magnitude formula. 85.887, okay, would be our resulting force. And notice that our forces were measured in pounds. So again, our resultant force would also be measured in pounds, right? Pounds of force. So there we go. Let's look at another example real quick. I'm going to jump here. Airplanes are always a good thing to think about with vectors, because again, we've got one airplane flying at 330-degree bearing. So what I'm going to do is kind of imagine on here, right? 330 degrees, again, around from north, right? It's going to put us kind of up in this area. That's what they're really telling us. And again, that one's going to be measured at a 520 degree or 20 mile per hour, right, force there. But we know we've got a 30-degree angle from that x-axis, right? North 30 degrees to the west, if you wanted to imagine it that way. Right? Then we've got the wind blowing though, and notice the wind is going to blow directly from the west, so it's coming in directly this way. So I'm going to position that right at the origin. I'm going to go 15 miles per hour, right? And again, that should be much shorter compared to that 520, but we'll get the basic idea here. But remember, if we want the resultant, what I'm going to do is draw the tip to tail method. I'm going to move that red line up here, right? So that our resultant force should essentially be drawn from the origin, kind of going up this way. Right, and if that 520 was much longer, this would be much a little more accurate. I'm just thinking we're going to end up there in quadrant 2. It sort of makes sense. But let's see what happens. Let's find that speed and direction of the resultant and see if we trust our picture at all. Right? So our first vector, again, remember, is a magnitude of 520. And we're going to say the cosine of our angle. Now what we need to remember is our angle has got to be measured from the positive x-axis. So we've got to measure from here over to that blue line, which remember we said this was a 30 degrees from north, right? 30 degrees west of north there. So I would say this is going to be a 120 degree angle, comma the sine, right, of that same 120 degree angle on there. Then we're going to add on, right? So plus, and remember the wind is blowing directly from the west, so that's at 0 degrees. So you could say 15 cosine at 0, sine at 0. I'm just going to call this 15 comma 0. It's nice when those angles are right on one of the axes, right? We get those nice numbers. And therefore your resultant, right, we'll just call it R, you could call it P for the plane, although technically that first vector would be more for more of the plane. But let's go ahead and find this. So we're going to be 520 cosine 120 plus 15 and 520 sine 120, again plus 0, so we don't have to worry about that. Okay. Now we can find that actual vector if we want to, but what I really want is the speed and the direction, right, of that vector. So what I'm going to go ahead and do is jump right to my formula and say, okay, well the magnitude is going to be equal to then, right, this 520 cosine 120 plus 15 squared plus 520 sine 120 squared. Now I can actually go find those numbers. It wouldn't be a bad idea, but again, I'm going to concentrate more on that magnitude. So let's go ahead and type all that in, and it might be easy enough to do so. We're going to say, again, 520 cosine 120, close the cosine, plus 15. And what I'm actually going to do is go ahead and store that as alpha A. And we'll see how that's going to be advantaged for us here in just a second. And notice that was negative 245. We may as well note that. Back to our calculator here, we need the 520 sine of 120. And again, I'm going to store that as alpha B. That will save me some typing here in a minute. But again, that's 450.333. So 450.333 on there. Well, that means that what I want for my magnitude is the square root of alpha A squared plus alpha B, right? Remember, that's how I stored those, squared. So that's 512.665. 512.665. And again, that would be in miles per hour. If I want the direction angle, remember that that's the tangent of B over A. So I could say that the direction angle theta will be the inverse tangent of 450.333 over negative 245, right? Or essentially inverse tangent of, again, the nice part is I've got those measures in there, so I can just say the inverse tangent of alpha B divided by alpha A. Save me some time there. Negative 61,452. Now I have a slight problem with that because that would be down in quadrant 4. And I'm definitely up here into quadrant 2, right? So don't forget I need to add 180 degrees. My inverse tangent gave me my first answer, and it was correct. Give me my reference angle down in quadrant 4, but I want to make sure I travel sort of 180 degrees from that. So I'm just going to add real quick here. 180. And we got 118.548. 118.548 degrees. And again, if you wanted that as a bearing, we would just have to reimagine that a little bit, from north, which you would just take a little bit of time to work your way around, right? 118 is going to be up this way. So maybe subtract the 90 and kind of work your way around, right, to doing that. Subtract 90 and then subtract that from 360 or whatever you need to do to figure out what that bearing would be. I hope that helps you with working with vectors and some real-world applications. Talk to your teacher if you have any questions, and have a great day.